Hello, everybody. Welcome. Looks like we're going to get started very soon. We'll give it a couple more minutes for people to finish streaming in. Hello, everybody. Good morning, good afternoon, good evening, wherever you may be. Welcome to today's webinar, Back to Basics, Understanding the WRM correction for non-Newtonian fluids. WRM being Weissenberg-Rabinowitsch-Mooney correction. So today you're going to be joined by myself as well as my colleague here, Dr. Sohaila, also known as Soha. So let's go ahead and proceed, shall we? Let me go ahead and click here for the following slide. So here is an overview, standard overview of what you're going to be seeing today. So instruments like viscometers and rheometers sometimes require this corrections to their measurements to get accurate results. So in this talk, we're going to focus on that one correction called the WRM, Weissenberg-Rabinowitsch-Mooney correction. And this correction is used to get more accurate viscosities of shear thinning or even thickening samples. So also known as these non-Newtonian samples. And these samples, specifically for samples measured with pressure-driven flows. So these pressure-driven flows, they're a common way to measure viscosity. Their advantages are high shear rates. You have a closed system, and you can even have ultra small sample volumes on the order of 10 microliters. So that's pretty low. That's very low, actually. That's less than a teardrop. So this is also relevant to us here at RheoSense because we deal with such pressure-driven flows. And of course, we often measure non-Newtonian samples. So it's important for us to have this WRM tool for getting more accurate viscosity measurements for these non-Newtonian samples. So in this webinar, we're going to be showing you the step-by-step on how to do this correction to get better viscosity measurement, to get better viscosity reading for many non-Newtonian samples. First, we're going to describe here, if you can see this top one, we're going to describe the differences and even examples between Newtonian and non-Newtonian samples. Then we're going to show how our VROC, viscometer rheometer on a chip, how this pressure-driven technology works, how we use it to measure the shear viscosity. Then we explain why for samples that exhibit this non-Newtonian behavior, why for these samples we have to correct the viscosity, which is, by the way, it's done by correcting the shear rate. Then we show the details on how to apply this correction to your data. And then last, we're going to finish it off here by showing examples of applying this correction to many different kinds of data. So what is the difference between your Newtonian and non-Newtonian fluid? This is going to be a review for most, if not all of you, but we want to include it as a little background for what we're going to show next. So this plot shows a cartoon of the shear stress versus shear rate obtained with a viscometer or rheometer. So depending on the instrument function, you can either control the shear rate and measure the shear stress, or the other way around, you can control the shear stress and measure the shear rate. So now to obtain the viscosity, we divide the shear stress by the shear rate, or the slope of this one here. And we have the corresponding viscosity versus shear rate plot here on the right. So for a Newtonian sample, the shear stress changes linearly with the shear rate, as you can see here. And this leads to the constant viscosity versus shear rate shown on this other plot. So now for non-Newtonian samples, you have this non-linear behavior. So well-known non-linear behavior like shear thinning or shear thickening that you can see in both of these plots here. So that's a brief intro into how Newtonian versus non-Newtonian, the behavior can show up, manifest, appear. So here, we're going to show some examples of common Newtonian versus non-Newtonian fluids. So common Newtonian fluids we see at rheosense are water, buffer, like PBS or histidine, etc. Buffer with excipients too. Organic solvents like IPA, xylene, toluene, what else? Heptane, DMSO even, NMP. And then what else? Mineral oils are also very characteristically Newtonian. And even dilute solutions of polymers and colloidal dispersions. So here are some examples now of common non-Newtonian materials. So these are now more concentrated colloidal solutions of polymers that are displaying this nonlinear behavior, especially as the shear rate increases. Also, colloidal dispersions will display this behavior at higher shear rates. So these colloidal dispersions include things like proteins, monoclonal antibodies, let's say. Also, microemulsions like creams and food products as well. So we here at rheosense deal with a lot of this shear thinning and non-Newtonian proteins, like these monoclonal antibodies, or MABs, we call these. So this shear thinning is occurring in your protein samples because the increase in shear rates jacks up the hydrodynamic forces, and this which then overcomes the Brownian forces that are acting to keep the local structure. So they're acting against it. So as the shear rate increases, these Brownian forces, they become saturated. They can't take it anymore. So they stop increasing, which means that now there's less resistance to your flow. So that's what leads to your shear thinning or your drop in viscosity in such protein samples like MABs and other samples as well. So also here we show polymer melts are another good example of these samples. And also any systems undergoing self-assembly like block copolymers, surfactants even, and this even includes proteins. So one last thing I want to point out is that these two are the same systems, but they start exhibiting this non-Newtonian behavior as the concentration is increased. So now for For samples that are exhibiting this non-Newtonian behavior, this WRM correction allows you to correct the shear rates, which in turn corrects your viscosity. So that's what it's doing. But first, I want to explain how our technology works. And this is so that you have a better idea of how this correction is going to fit into this. So VROC, again, stands for this viscometer and rheometer on a chip. And viscosity is measured on this microfluidic channel within all of our instruments. So this is a rectangular channel that can have any thickness you prefer, anywhere from 20 to up to 300 microns. Generally, if you increase the thickness, you can measure high viscosity samples at low shear rates. So like, very high viscosity, we have many examples of high viscosity oils, or we even measured mayonnaise one time. So as the fluid is flowing through your channel, you have these four MEMS pressure sensors that are detecting the linear drop in pressure along the channel. And then from this pressure drop, we get the shear stress. As you can see here, this is the pressure drop. These are the dimensions of the channel, and you get the shear stress. We also have direct control of the flow rate, which gives us the shear rate. So this is the flow rate, this is the shear rate. And therefore we measure the shear viscosity, which is that shear stress we have measured divided by the shear rate that we controlled. So this shear viscosity is this resistance of your sample to this shear deformation. You're trying to deform it by shear, but it's resisting, and that's what is measured by the viscosity measurement. So it's this resistance of how the sample is flowing in the channel. So this is viscosity is what the instrument is reporting, and this is the true viscosity for any Newtonian sample. So we don't need to do any other corrections with our VROC technology. That's the true viscosity. However, for a sample that exhibits the non-Newtonian behavior, like shear thinning, this is not the true viscosity. This is the apparent viscosity. So this leads us to the question here: why do we have to correct the shear rates and thus the viscosity for these samples that exhibit non-Newtonian behavior? That's the question we have. So let's go ahead and continue there. So let's start explaining why we need this correction for the shear rate to get the true viscosity. So this is a cross section here of a rectangular channel. So it's showing the velocity of the fluid across the channel. So as you know, we push the sample through the channel. So this is this pressure-driven flow. And because of these confining walls in the channel, the velocity of the fluid at the wall is 0. However, the viscosity in the middle is the highest. So it's going from the highest in the middle down to 0 at the wall. So this is making assumptions that there's no slip in the walls, the flow is laminar, no secondary flows. And these conditions are met with our microfluidic technology, and with 99%, like 99.9% of all the samples we measure, there's no slip in the channel. So we can think of this shear flow a slightly different way. We can think of this as adjacent fluid layers that are moving past each other, while the middle layers are moving the fastest. I like to think of it that way. So you can think of this as a deck of cards you see here. You can see that in the middle, the layers displace the fastest, while this outer layer over here, for both sides, the position is the same as it was initially. So what is the shear rate? The shear rate is how much this velocity is changing as you move along this cross section. So as you move along this middle part, the velocity is not really changing. There's a constant here. So the shear rate there is 0. But as you move along these edges over here, so these edges here, the velocity there is changing the most. So the shear rate there is a max in the channel. So this max shear rate at the walls is what we calculate for our measurements. This is because that's where we measure the pressure. We measure the pressure directly at the wall. So for a Newtonian sample, the velocity profile is parabolic, like you see here. And in this equation, we used to get the, and this is the equation we used to get the true shear rate for Newtonian samples with this parabolic profile. Now, this equation, therefore, is derived based on the sample being Newtonian. That's how it was derived. Now, for your sample that's shear thinning, which are non-Newtonian, we can no longer use this equation to get the true shear rate. And this is because the velocity profile for these samples is no longer parabolic. So for these samples, the true shear rate at the wall now is higher than expected, based on it's higher than expected from this Newtonian calculation of shear rate. So this is why we need to have the WRM correction, which is going to give us the true shear rate in order to get the true viscosity for these cases, non-Newtonian cases. So here we finally get to the, we go through this showing how the WRM correction is done for our data. So here we show one of our data sets of viscosity versus shear rates. And for review, just a quick review of the shear stress, we obtained it from the pressure drop. So no correction is needed for that, for our VROC technology. For some other pressure-driven devices, you may still have to correct them, but not for VROC. So as mentioned before, the shear rate for non-Newtonian fluid is given by this equation. So this subscript N is for Newtonian. And this is what the software, the VROC software, is reporting as the shear rates. But for a non-Newtonian, non-linear sample, this shear rate needs a correction to be made more accurate. So let's look back at the data set. So this data set is showing both a linear and a non-linear shear thinning region. So since we have at least enough data points here, we can perform this WRM correction. So we need at least 3 data points to do it. So to do the correction, we first have to take this data here and plot it, the log of shear rate versus the log of shear stress. So that can easily be done. And then we fit this with a quadratic. So quadratic fits the data well. So that's it. So now you can correct the shear rate using this expression shown here. So this is the WRM expression. If you want to see the derivation for this, it's very simple. The best derivation I've seen so far is from this rheology book known by he's actually a well-known professor, McCoskell. We've actually worked with him before, and I would say this book is a must read for any rheologist, I would say. So even though you can access this book online for free, I highly recommend you get a physical copy if you want to go over all these things. I often found myself flipping back and forth on this book as I took notes. So, all right, back to this. This WRM expression is what we'll use to correct the shear rates. This expression is valid for this rectangular channel we have. In the textbook, you can also find an expression for a circular channel, like the needle of a syringe, if you're interested in that. So we basically take the derivative of this equation here, and that's it. So for each shear stress, now you can calculate the true shear rate from the Newtonian or apparent shear rate. So now once you have the true shear rate here, now you can use this to get the true viscosity. So here we have now on the top right, the uncorrected data in blue plotted with the corrected data, and we can see that the corrected data is shifted down and to the right. So this makes sense why it's shifted like this, because the true shear rate, as you can see here, is actually greater than the apparent or Newtonian shear rate. There's the velocity is changing much faster here. So, and because the shear rate is higher, of course, from this equation, the true viscosity is going to be lower. So that's how we do this correction here. And then for the next part, my colleague here, Dr. Sohaila, is going to show you how to automatically apply this WRM correction to your shear thinning samples to get the true shear rate and true viscosity. So she's going to show you this with our RheoSense Clarity data analysis software. And she will show you this for multiple types of samples. And then she will show you other features as well, like modeling with Kuro-Yasuda and cross model, etc. So I'll stop talking. I'll leave the floor for her.
Thank you, Christian. Hello, everyone. Thank you for the great introduction and background on WRM correction. So with that in mind, let's now move on to a quick demo of Clarity to show how we can analyze data with this tool. Before we get into the demo, I will provide an overview of the features and types of analysis that can be done with Clarity. However, for today's webinar, we will focus specifically on WRM correction and show you how this process works within Clarity. The new version of Clarity that has been released recently is a powerful tool for data analysis. In addition to WRM correction, which is the primary focus today, Clarity also allows for intrinsic viscosity analysis, giving us insight into not only the intrinsic viscosity, but also the molecular size of your sample. Another exciting new feature in Clarity is injection force analysis for drug formulations, MABs, and proteins. We know that most MABs and protein samples exhibit shear thinning behavior, and it's crucial to factor this when calculating injection force. Without considering shear thinning, the injection force calculation could be inaccurate. To do this properly, we need to measure the viscosity of our protein sample over a wide range of shear rates to capture this shear thinning behavior. So once the data is captured actually with VROC technology and is loaded into Clarity, it performs all the necessary calculations and provides an accurate injection force based on the full viscosity data and syringe geometry. Clarity also includes model fittings like the Ross-Minton and quadratic models for viscosity versus concentration data. And also for shear thinning samples, it offers models like Kuro-Yasuda and Cross, which can help us better understand things like the onset of shear thinning, primary plateau, and power law index, insights that are hard to get directly from the rheometers and viscometers. So we can extract these information by using these models. All right, now let me walk you through the step-by-step process of using Clarity for WRM correction analysis. First of all, after completing your measurements, if you have Initium or MVROC2, you can export your data as database file. So make sure to export it as database and not Excel or CSV, because for this instrument, Clarity does not support Excel or CSV. So once your data is exported and saved, open Clarity, import the data file into the software, select the data and click load. Then after loading the data, simply select it and click analyze to move on to the next step. So once you click on analyze, you will be directed to this page where you can see all the individual segments along with key information such as viscosity, shear rate, flow rate, and R squared, which actually R squared indicates the quality of your measurement. And R squared value close to 1 means the measurement is very good, while a low R squared could suggest an issue with the data, like a clog in the chip or improper cleaning. So if you click the graph icon next to each segment, you will open the viscosity versus time graph, also known as transient curve. This graph has two main parts. The first part shows viscosity increasing until it reaches the plateau, which we refer to as the wait time. I mean the time it takes to reach the plateau viscosity. Once the plateau is reached, the software starts taking measurements, which are shown by these green symbols on the graph. So the viscosity for each segment is the average of these measured data points. As you can see, Clarity allows you to get much more detailed information about your data. Also, Clarity includes filtering options based on predefined criteria. So it automatically excludes priming segments from the analysis and also can filter out bad data as well. For instance, if there are some bubbles in the sample, this can lead to inaccurate data. These segments will be highlighted in pink and excluded from the analysis. Take segment 10 in this data series, for example, it's highlighted in pink because it's been excluded due to bad data. So if we look at the graph more closely, we can see a drop in the curve, which could be a sign of a bubble in the sample. So thanks to Clarity's filtering feature, this segment is automatically removed from the analysis. However, Clarity also gives you the option to reprocess the data. So even those problematic segments can be reprocessed and can be used if needed. Now, if we click on proceed to analysis, which is shown with arrow, we will now be directed to this page where we can plot and use the appropriate features to analyze our data. For example, we can average our data based on shear rate. If we run our sample multiple times at each shear rate, let's say 3 times, we can use the segment averaging feature to take the average for each shear rate. After averaging our data, we can select the data for a specific run by clicking the checkbox, which is shown as step 1 here. Then we click on the graph icon shown as step 2. When we click that, the new series window will appear, prompting us to enter the sample name. For example, here I named my sample as cream because I was testing hand cream with Enviroc2, and I exported the data as database file and imported into Clarity to analyze my data. Once we enter the name, we simply click continue, and now the series configuration window will pop up, and from here you can choose to apply WRM correction to your data. So as you can see here, we also have IF analysis that stands for injection force, and IB that stands for intrinsic viscosity. So after you choose WRM from this analysis box, you can simply click on the WRM option, and then software will automatically handle all the calculations and analysis that Christian covered in the introductory slides. So then you can click on close, and here, then you will be directed to this page that you can see the viscosity versus shear rate graph for your sample. Here I tested, as I said, I tested Nivea cream measured with our NVROC2 and C20 chip. So the dark blue represents the uncorrected data, while the light blue circles show the data after WRM correction. So this is a very high viscosity sample, but it shows a strong shear thinning behavior with apparent viscosity dropping from, say, 9,000 centipoise to 600 centipoise as the shear rate, apparent shear rate increases from 20 inverse second to 1,300 inverse second. So as you see, in this case, WRM correction makes a significant difference. After correction, the shear rate shifts to higher values, while the viscosity shifts to lower values. For example, after correction, the shear rate starts at 35 inverse second, and the viscosity starts at 5,500 centipoise, then decreases to something about 400 centipoise. So to get to the true viscosity, we first, as Christian explained, we first correct the shear rate, and then we can calculate the true viscosity by dividing the shear stress by the true shear rate. Keep in mind that the true shear rate will be higher than the apparent shear rate, while the true viscosity will be lower than the apparent viscosity. And WRM correction does not change shear stress. And it will remain constant actually in our instrument. Clarity also generates a table that includes all detailed data such as apparent shear rates and viscosity, as well as the true shear rates and true viscosity. So I would like to present another data series collected for 5 weight percent polyethylene oxide with a molecular weight of 200 kilodalton, along with the data after WRM correction. The data you are seeing here is a combination of 2 chips, BO5 and EO2, to cover the full shear rate range. As you know, we offer different chips that are designed for different shear rate and viscosity ranges. For example, BO5 is typically used for lower shear rates, lower viscosity samples, while EO2 is ideal for higher shear rates measurement. Sometimes to fully understand our sample, I mean, if we want to understand our sample at both low and high shear rates, we need to use 2 chips. For example, in this data set, if we only run the sample with the BO5 chip, we would only detect the Newtonian plateau without seeing the shear thinning regime. However, after running it with the EO2 chip, we were able to capture this shear thinning behavior. As seen, the apparent viscosity drops from 45 centipoise to 22 centipoise, and while the WRM correction does affect the shear rate and viscosity, the change is less dramatic compared to the cream sample, which had a very high viscosity and exhibited significant shear thinning. So as is typical with WRM correction, we see a decrease in viscosity and an increase in shear rate after correction. So the last data set I want to discuss with you is related to protein samples. Viscosity data for protein samples is always interesting as they typically exhibit shear thinning behavior. As Christian mentioned, we observe shear thinning in high concentration protein or MAP solutions. Therefore, WRM correction should also be applied to these samples to ensure we get true shear rates and true viscosity. Here we have data from the EO2 chip that shows the shear thinning properties of the MAP formulation. We usually run protein samples with both the BO5 and EO2 chips. The BO5 chip captures the Newtonian plateau, while the EO2 chip captures the shear thinning region. Here we are showing the viscosity versus shear rate before and after WRM correction. In theory, WRM correction doesn't change the data in Newtonian plateau, and it only corrects the viscosity and shear rate in the shear thinning domain. Therefore, WRM correction can be applied only to the data from the shear thinning domain. For this specific map solution, viscosity drops from roughly 80 centipoise to 50 centipoise as the shear rate increases from 1,000 inverse second to 30,000 inverse second. As you can see, the map exhibits shear thinning behavior. It's very obvious, which has a significant impact on the injectability of the formulation. So if you want to use your viscosity data for injection force analysis, please keep in mind that you need to have the full viscosity curve of your protein sample to be able to calculate the injection force more accurately. To summarize, after today's webinar, we now have a clearer understanding of WRM correction and how Clarity can easily correct the data with just one click. It's a user-friendly tool that generates a PDF report containing all the data and associated graphs. So I think I will wrap up the webinar here, but please feel free to submit your questions in the question box and we will address them. Thank you.
Thank you so much, Soha. So let's see if, feel free to add your questions if you have any. Looks, yeah, we have a lot of attendees today. That's great. Looks, we had a lot of interest in going back to the basics, WRM correction.
Yeah, that's amazing.
We hope you learned more about this method. And let's see, looks like we have one question. So is Clarity Windows 11 compatible? Yes.
Yes.
And the short answer is yes. It's compatible. Oh, it looks like there's more questions. Good. A lot of questions. Okay. So a question is, how do you verify that rheology after the correction factor is correct? So we have an application note where we compared the data from Conan plates with the viscosity obtained with that technique, comparing it to our technique, VROC technique, before and after we applied the WRM correction. And we saw that there was agreement between both instruments after applying the correction. So if you want, we can send you that app notes. It's also available on our website. So we have, I think, multiple WRM app notes available there. You can go there and search. We made it easier to search for those. So for Clarity's filtering option, so if I have bad data in between 20 runs, for example, run 17, can I use the filter and still get a better curve?
Yes. So you always can reprocess your data. So the Clarity, if it's bad data, if Clarity determines that your data segment, for example, 17, is a bad data, it will remove it from the analysis. But if you still need to use the data from segment 17, you can use the reprocess feature, and Clarity does the reprocess for on your data, and then it gives you a data and it filters that bad data points in the graph and just keeps the good data points and gives you a new data for that segment. So still you can use reprocess feature and do analysis, extra analysis on your data and get good data.
There's another question about So this is summarizing it about compatibility with our instruments. So it's compatible with our Initium instruments. It's compatible with the MBROC2 database. It's also compatible with the first MBROC, so with the Excel file you get from that. It's currently not compatible with the microvisc, but we can certainly add that if we get as we get requests. Let's see. Looks like there's.
So for MBROC1, if it's there is a question for compatibility with MBROC1, you still can use Clarity with MBROC1, and in that case, you have to export your data as Excel, and Clarity supports that for Excel and MBROC1 database.
Yeah, that's right. You import your Excel file and you can analyze it here, just like my colleague showed you. There's another question about injectability, doing injectability analysis on this Clarity software, if that is still possible. So yes, we can do that. We didn't go over the details today, but that's possible, and it shows you very accurate estimation of injection force. And I say accurate because we've compared before with the monoclonal antibody series. We compared measurements between an force gauge, so instron force gauge, which requires a milliliter, so much higher volumes than we use. We compared those forces to the ones we estimate from the viscosity measurements, and we got good agreement between those two. So we can, we have that information available. We can send that to you if you'd like. So I have there's another great question here. The WRM correction information was great. Well, thank you very much. That's very nice of you. I have a question that is semi-related. How do you mitigate evaporation in high concentration protein samples for longer sequences? So if you're running longer sequences, so I think this is related to the Initium instruments. So for longer sequences, which can take on the order of more than an hour, what we do is we set the temperature in the tray. So I'm assuming you're familiar with all these components. You're setting the temperature in the tray to, so what we set it to typically around 10 degrees Celsius. And this, we've seen that with that 10 degrees Celsius, we mitigate, that a lot of that evaporation. And we've actually done these studies before where we run 96 consecutive samples at a time. So we can run with a 96 well plate. The same sample, just 96 different times. We set the tray to 10 degrees and we see that the viscosity is consistent. However, if we had set that tray to 20, like room temperature, we would have seen a slight upwards trend in the viscosity. So that's a good way to mitigate this by setting the temperature in the tray to, I recommend 10 degrees. So another question is, how can one obtain the shear stress and yield stress for a non-Newtonian fluid if the viscometer only reads viscosity and shear rates, assuming a power law or HP model? So when it comes to yield stress, that's a little more tricky to obtain with our instruments.
Because we need to have shear rate very close to 0. And so it's a little complicated to obtain it with like VROC technology. Yeah,
it would be, if we can obtain it, it would be more likely for those higher viscosity samples with our chips that can go, to very low shear rates. So I think minimum shear rate we can go down to is on the order of seconds, so 1-2 seconds, inverse seconds, that is. So there you're more likely to get the yield stress, but it's not really, it's tricky to get the yield stress here, as
tricky.
opposed to like a controlled stress rheometer that gives you, you know, a nice value of shear stress depending the sample. Another question is the shear rate versus viscosity plots from the measurement of one injection of sample? Yes, that is correct. So we inject one sample and we measure multiple shear rates with the same sample. So we set in the measurement protocol, we want 10 shear rates or 15, however many you saw, and it'll run one after the next. Now with our MVROC, with the old MVROC 1 instrument, you need, you know, you have to be worried that it runs out of sample. So you have to reload the syringe again. But with our newer instruments, like the MVROC 2 or Initium, you can use one small sample, like 90 microliters of sample, and it's going to run all those shear rates for you with just that small volume. And that's thanks due to our retrieval feature. So once the sample is emptied from the syringe, it's retrieved, it's back pressured, and again, you can measure over and over again. We like to see unlimited measurements that you can get from that small volume.
Yeah, we have measured, for example, one sample for like 1,000 times. So we only loaded 90 microliter of the sample, and we did 1,000 measurements with that 90 microliter of sample. So you can do extensive measurements, and if you are interested in more advanced rheology analysis of your sample, you can easily do it with our fully automatic Initium or MVROC 2, since it allows you to run your samples for unlimited times, so can get more information.
The question is, will the slides and recording be shared? So the recording will be shared. We will also post it to our YouTube channel, the Viscosity channel. And the slides, we can share those with you if you'd like. Please send us an email and we'll share those. We'll share this with you. And then another question we have here is like heavy crude oil emulsion. So I personally haven't tested heavy crude oil emulsions here, but this is something we can work on with you to test. So if you send us a sample, you can work with one of our team members here. We'll get a sample, and then either my colleague here, Soha, or me will test to see how we can clean the sample from the channel. That's very important. So we often do this. We do this with, we've measured like other samples like slurries, battery slurries.
So yeah,
we measured a wide range of samples, and we can work on the development so that it takes the work out of you. We take the guesswork out of you, so that way when you run your sample, you just, you know, all you have to worry about is the shear rates you want. And
yeah, definitely we are able to measure a wide range of viscosity, especially with our new viscometer MVROC 2. Recently we measured a sample which was about 80,000 centipoise, so very high viscosity with our MVROC 2. So
what are the implications of zero shear and negative viscosity results? So zero shear, I think you may be referring, I think I know what you're referring to. The more common term for zero shear viscosity is, you know, what is the viscosity at zero shear, which you can estimate from modeling, you know, fitting the viscosity versus shear rate data, and then you extrapolate to zero shear and you get that viscosity. Now, if you're referring to our instruments, so in our instruments, when you make a measurement protocol, you can set the shear rate to be 0. But what that does is that you're telling the instrument to measure automatically for you. So if you put 0 in the measurement protocol, the instrument is going to select the shear rate, a shear rate for you, and it does this based on you know, how much it wants to make sure it doesn't overpressure your chip. So it runs at about 50% of the pressure of the chip, and it does that for you. It's like, we call these automatic measurements because, you know, if you want to just run your sample, you don't care about the shear rate, that's a good thing to do, to run automatic measurements. Now, you mentioned negative viscosity results. So in one of our instruments or a couple of instruments, sometimes your viscosity column can report if there's an issue with your sample, you know, maybe you loaded too many bubbles. There's a chance that the unit may detect, may not be able to get a good plateau of your viscosity. So in that case, it'll report a -1, but you still have that data available for you. You can export that data to Clarity and still get a viscosity value. So it doesn't mean there's any error in your instrument. How do you prevent or manage torque overload in your rheometers, especially for highly viscous samples? So we have, in this case, so there's a torque rheometers, and then we have this corresponding pressure. So we rely on pressure. So torque is just force times distance. Yeah. We have pressure, which is force divided by area. So in that case, the question would be, how do we manage pressure overload? And we have a very robust system, and I'll let my colleague Sohaila talk about how we manage overpressures in the chip. So we have a very robust system. And
so yeah, there is a logic in our software that prevents like the overpressure in the system. For example, as I said, our advanced viscometers like Initium and Envirog2, they in the software we have overpressure logic, and if for example you want to push your high viscosity sample at high flow rate, the system gives you warning. It doesn't allow you to run your sample. It gives overpressure warning, and it in some cases, if you are in the middle of the measurement, it can adjust the flow rate for you. So for example, if you set your flow rate at very high flow rate because your viscosity is high, so the system does not run your sample at that high flow rate because it can overpressure and it can damage the chip. However, what software does is that it adjusts the flow rate. So depending on the viscosity, it recalculates the flow rate and it reduces the flow rate, and it runs your sample at that adjusted flow rate, which is safe for the chip and for the system. So yeah, with our advanced software and advanced instrument, you shouldn't be worried about this because everything is under control, and software and firmware can control the this overpressure issue for you, and it has overpressure handling, and you shouldn't be worried about this.
Great, thank you. So we'll give a couple more minutes for any additional questions. I think we have a few more. I'm looking for them here.
I think we addressed all of them.
So there was an earlier question about verifying that the data is correct after the WRM correction. So we mentioned that you can compare. We have an app note where we show how we verify that. Now for Newtonian samples, to verify that the chip is calibrated, a common way is to use a viscosity standard. So we use a viscosity standard and we measure for the entire range of the chip. So pretty much the entire range that the chip will go, as you're going from low to high shear rates. And we verify that matches the viscosity we're getting matches with the viscosity standard. So somebody saw an event coming up from RheoSense. I think they're talking about the end user forum. It's we have this end user forum in I think April.
Yeah.
April. So it's a very nice event. We have a lot of end users attend. There's a lot. We have talks. Food is included. There's a happy hour as well. There's a lot of chance for interaction with us at RheoSense. You can even come to the office. We can show you the instruments. It's a very nice event. If you have the time and the chance to attend, I would recommend it. And it would be great to have more, as many people as we can here. It's always great to have a lot of attendees. So that's in, I think it's early April. I think it's the first or second week of April. It should be in our website already. And you may, if you're in the email system, you may get an update. So it looks like I'm seeing here it's April 8 to 9. April 8 to 9. So hopefully, if you want to attend, if you can attend, that would be great if you can make it for those days.
Yeah, definitely, it's a very good opportunity to connect with like rheologists or.
That's right. Yeah, we're going to have a lot of. We're going to have speakers from different areas. So we have a rheologist speaker from Craft. We're going to have like a few other speakers from other. I have to check the list, but it's another speaker from biopharma, another one from who's an expert in viscosity measurement. So Dr. Shoup from Stratum. So he's he has a company in San Diego. They work a lot with these biopharma products, and he's very knowledgeable about these viscosity measurements and how to translate your viscosity measurements to the applications in biopharma. Oh, there's actually another question. So I have two questions here. One of those, I'll answer the forum one first. So the one question is, where is the forum conducted? So that's conducted here at RheoSense.
In San Ramon, California.
In San Ramon, we have there's like a place nearby here. It's very beautiful. It's has a big rooms for enough space, and it's very nice. Very nice.
But the location will be California, close to San Francisco.
Yeah.
So if I want to just generally answer the question.
Thank you for that. You mentioned, okay, so now I'll get to this other question. You mentioned you use standards for system suitability. What standards do you typically use? We are using 10TP aqueous MGVS, and it works well, but it's hard to tell if it is appropriate for higher viscosity samples. So that one is good. MGVS 100 or 10 centipoise MGVS is good. I think you have an initium instrument, and that works well for no matter if you're measuring low or high viscosity samples. So maybe you're asking why is it good for high viscosity samples if this is a 10 centipoise standard, right? So the reason for that is because with this 10 centipoise standard, we probe the entire pressure range of the chip. So and this entire pressure range of the chip is what you're going to be where you're going to be working with when measuring these high viscosity samples, right? So once you calibrated this entire, you verify this entire range of the chip that it gives you the right viscosity, you're good to go for these low or high viscosity samples. Another question is, do you guys prefer MGVS or mineral oil? So for like instruments like initium, I can talk about initium. We recommend MGVS. That does very well. Mineral oil, we've also calibrated with mineral oils. That's a good option. You just have to make sure you use the right cleaning solvent. So we typically use heptane and acetone. I don't know.
Yeah, that's true. So even if you want to use mineral oil on initium, you should make sure that choose the right solvents for cleaning, like heptane, acetone. So since maybe most of the customers are dealing with protein samples and they already their setup actually is for cleaning the protein samples. Maybe for that, for those cases, MGBS would work better. So because they do not need to change the solvent bottles when they want to calibrate. So there, I think there is no preference, I would say. So, but here, when we do the calibration and when we issue certificates for chips, we use mineral oils, but there is no preference. You can use either oil or MGBS.
Okay, perfect. So it looks like it's on the hour now. We don't want to take any more of your time. Thank you guys so much. Thank you so much for attending and for your questions. It means a lot to us just seeing your engagement and just you attending, being present. Thank you guys. When hopefully we see some or a lot of you at the user forum. It's a very nice place, this user forum. There's a lake next to it. It's beautiful. There's a lot of trails here. And of course, the user forum itself, there's going to be a lot of great content and information you may want to know.
Yeah.
Awesome. Thank you so much, Justin. Yeah. We love seeing you around, Justin. All right, thank you guys. We're going to go ahead and finish the broadcast here.